for lab today, because we haven't talked about AC impedance yet, I'm going to go through explaining how AC impedance works, and then I'm actually going to do the experiment and I'm going to do the experiment, but have you record the data yourselves and do the work. So it should go a little quicker because I'm going to be actually collecting the data, but still you're going to do the analysis part. So we're looking at AC impedance, AC alternating current. We have inductors, resistors, and capacitors. And the voltages across these are not in phase. We saw yesterday in class that the voltage and the current were out of phase by 90 degrees. Remember, I had them backward, which one was which? And after reviewing it, like I told you I was going to have to, when we write the equation, we don't put that minus sign there. The minus sign, remember from Faraday's law, we had that minus sign is part of our sign convention, but we take this equation to write the voltage drop across the inductor is equal to L, change in current, over change in time. And your L would have to have a minus sign in it. It'd have to be negative inductances for everything if you kept that minus sign there. But the minus sign, we said, was only to remind us to look at Lenz's law for which direction the current's going to be. And so using our definition of if the current's going like this, then that's the plus and minus signs. We don't have the minus sign in this equation. And that's why I had the signs, I had wrong which one was leading, the voltage or the current. But they're out of phase. Now let's just take a practical peek at real data and then come back to talking about the theory. So real data, go to Pasco here. Okay, so I'm collecting, move out of the way, come on. I'm collecting data here of the voltages across a whole bunch of things. I have, if you notice here, 5 voltages. V0 is the voltage from the source. That's the voltage I'm putting into the circuit. Generally, you'd think the voltage going into the circuit should be the maximum voltage, right? Because everything's a piece of that. But because of the different phases, that's not the way it is. If I highlight the color there for the total voltage, that green line is the total voltage. And you see that's far from the highest voltage. The highest voltage is whatever that purple one is. So let's go through what the other voltages are. We have this here is the voltage across the resistor. Now the voltage across the resistor is just IR. So the voltage across the resistor needs to be in phase with the current. That is, the peak of the voltage should be the same time as the peak of the current. But look at the peak of that purple one compared to the green one. They're close, but they're not the same place. So the voltage coming out of the power supply and the current coming out of the power supply aren't even in phase. So that's the voltage across the resistor. Then I have the voltage across the inductor. Notice the voltage across the inductor has its peak voltage before the current, which has its peak with the voltage across the resistor. Question, Larissa.
Can you turn off some of these lights so we can see?
I can turn off the rest. That help?
Yes.
Okay. Sorry. Okay, so this here, the VB is the voltage across the inductor. The inductor was first in its peak, came at the earliest time. Hence the Eli from Eli the Iceman. E stands for voltage, EMF. L stands for inductor, I stands for current. So the voltage is going to be at its peak at an earlier time than the current for an inductor. Now, if we go to the capacitor, we have the peak. The hand there is showing where the peak, well, actually this one here. This is where the current peak is, and the voltage peak is later for the capacitor. That's where ice is. Current leads in a capacitor, the voltage, the EMF. And notice where the peak for the capacitor is compared to the minimum for the inductor. the inductor and capacitor are essentially 180 degrees out of phase. When one's at a peak, the other's at a minimum. This final one is the voltage across both the resistor and the inductor. You look at that voltage across the resistor and the inductor, which one's it closer to being like, the resistor or the inductor? Yeah, it's right beside the inductor one. And that's because the voltage is much bigger here for the inductor than for the resistor. So we have all of these different voltages through the circuit. I'm going to stop it here. At any one time, so for instance, where this vertical line is here, at this time, if I add up all of the voltages for each piece, so I have to throw out the blue one because that's a combination. But if I add up everything that's not the blue one and not the green one, it needs to add up to the green one, because that's what Kirchhoff's voltage law says. Go around the circle and add up all of the voltages, it has to add up to 0. So that means at this time, this negative value plus this positive value plus this positive value has to come out to equal this very slightly positive value. So that's what the practical data looks like. And we're going to make our measurements of this. Well, let's make the measurements right now. So everybody ready to be a scribe? So I'm going to turn the lights back on so you can see as you be, whoops, wrong lights. So you can see as you be scribes and write these down. So I'm going to measure each one of these voltages and make sure you have these written down and with uncertainties. So for the source, trying to find the peak here, it should be a green box with an arrow that's vertical when I was moving it. So the source is, it shows 9.959. Now, I don't think I'm good enough to get that last digit, so I just go with 9.96 plus or minus 0.01, right? Because just my little hand shaking is enough to make it significantly different as I move it around. Okay, so that's voltage source. Then we'll go to the voltage across the resistor. So put V with a subscript of capital R. So the voltage across the resistor has its peak of, that doesn't seem right. Come on. Three point 3.337, which I would say 3.34 plus or minus 0.01. Then the voltage across the inductor. I think that's good. 12.01. Voltage across the capacitor, 15.98. And finally, the voltage across the resistor and inductor. So put V subscript of capital R plus L. And that's 12.62. You wrote them down, right, Yafet? Because Yafet's going to be great, and he's got to have the number so he can do it right. So we have the voltages for each one of these. Now, if you look at them, you can verify. If you were to take the voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor, those add up to a whole lot more than the voltage from the source. Why is that possible? That's one of your questions to answer. Why is that possible? What did we just measure? We measured the peak voltages, but they don't have their peak voltages at the same time. When the capacitor has its peak voltage, the inductor has its minimum voltage. So we can't just add the peaks up and expect them to give us the input peak. We have to take into account that these are at different times that we're making the measurements. You know, that's like me saying, Well, I had $100 in my bank account. This time I had $100. This time I had $100, and this time, so I say have $300. Oh, that I wish it worked that way, but no. Okay, so we have our measurements, and then let's learn what to do with them. So back to theory. Here's graphs just showing those curves we looked at in isolation. The current there is in green, so you can say, okay, if that's the current, then what's the voltage through the resistor like? And notice the voltage is right in phase. You have a peak in current, you have a peak in voltage through the resistor. But at that same time, you have 0 for the voltage through the inductor and capacitor. And the total voltage at that time has to be the sum of all of those. So it's going to be the voltage through the resistor plus 0. It's just the voltage through the resistor at that time. But you go to the time when the resistor is at 0. Perfect. I have the steadiest hand this side of nowhere. The time when the current is 0, you have maximum negative voltage for the inductor, maximum positive voltage for the capacitor. You add those together to get the voltage at that instant for the total voltage. And so that's what we saw demonstrated before. Now, people in class earlier today saw me do my hand drawings of this. What we have is peak voltages across each one, and then the actual voltage is varying with time, and we can take it as if we're taking the projection of a vector in the x direction. And that vector is rotating in a circle. And if we just look at the x direction projection, that's going to be a sinusoidal variation. But because the voltage peaks at different times for capacitor, inductor, and resistor, we have to set them at different angles for comparison. So this picture is showing the voltage across the resistor at 90 degrees from the voltage across the inductor, with Eli, the voltage across the inductor is 90 degrees ahead. And then we have the voltage across the capacitor, that ice, 90 degrees behind. And so then you just have those going around a circle, and you take the projection in the horizontal direction, and that tells you what the voltage on the entire circuit is going to be. So we have these three vectors, and they're adding together. How do you add vectors? Tip to tail. So if you want to find the total voltage, you just add these vectors tip to tail. Who wants to do it slope like this? What's easier? Rotate them so you have horizontal and vertical, right? So by convention, since that tilt is only to illustrate that this rotates, we do our vector diagrams, our Phasor diagrams, call them phasors because they're phase vectors. We're using a vector to represent that they have different times when they are at their peak, which we call their phase. So we take these Phasor diagrams and we put the resistive voltage in the horizontal direction, the inductive voltage going up because it's 90 degrees ahead, the capacitive voltage going down because it's 90 degrees behind. And then you just add them like vectors, so you add them tip to tail. So the total voltage will just come from adding those together. You get your resultant. You can measure this phase angle. We use the Greek letter phi because that's F in Greek for phase. And if you look at this, cosine of that phase angle should equal, what's cosine always going to equal for right triangle? Blank over blank. Adjacent over hypotenuse. So that'd be r over the hypotenuse for the right one. The hypotenuse is labeled Z. Z stands for the impedance. The impedance is the total resistance to charge going through. Now, resistance was taking away energy. But inductors and capacitors don't take away energy. They store it and give it back. So we call what they do a reactance. And so we have for an inductor, V is equal to Ix sub L, where X sub L is equal to omega times L. Omega is the angular frequency. Remember, by definition, omega is 2 pi f. And L is the inductance. What are the units of X sub L? Ohms. For a capacitor, V is equal to I X sub C, where X sub C is equal to 1 over omega C. Once again, X sub C is the reactance in units of ohms. These reactances, because we put voltage of the inductor vertical, the X sub L would also be plotted as a vertical. Voltage capacitor is down, X sub C would be down. And so we find Z is equal to, using the Pythagorean theorem, resistance is horizontal, and then we have XL up minus XC down. That's what the impedance is actually measured as. So the impedance is the combination of the reactance, which is in the vertical direction on our Phasor diagram, and the resistance, which is horizontal, and then we just use the Pythagorean theorem. We could have also used this graph here to find phi. In this case, we would have had cosine of phi is equal to the voltage across the resistor divided by the voltage total. Because the voltage total was in the horizontal direction, was the hypotenuse, and the voltage across the resistor was horizontal. So hey, look, these equations look very similar. What's the difference in what I did? I did it in impedance. In my lab guide, which I also wrote, I did it in voltage. But you can see that these are the same. Oh, I used tangent here. Tangent is just going to be opposite over adjacent instead of using the hypotenuse. So it's the same idea. And here's those equations for the two impedances. Now, with the impedances, what is the impedance really telling you about? Its unit actually is a good clue. Or its name, reactance. Yes, I meant reactance. Wow. And it's not its unit, it's the name reactance. What is reactance telling you about?
How it reacts to the current.
How the voltage reacts when you put current through. Perfect. It's not doing what it did with the resistor. With the resistor, it absorbed energy, and hence we called it a resistance. With the reactance, it's reacting, it's storing energy and giving energy back. And so that's what the reactance is telling us about, is about energy storage and return. And the impedance is combining those two ideas. So if we look at the inductor, if the frequency is really low, how does the inductor react? If you put current through, what does it do? If F is approximately 0, then what is X sub L? It's approximately 0, which means that it does nothing. It doesn't react. Why? Well, how do you make an inductor? Physical construction of inductor, what do? You wrap wire in a loop. Well, if you have just a constant current going through a wire, that wire should have very minimal resistance and thus should not affect you. Now, in reality, there is a certain amount of resistance in the wires. And furthermore, in our inductor that I'm using here, it has a metal core. It has the metal core because it increases the inductance. But when I put a current in there, it creates a magnetic field. There is actually a physical rotation of the magnetic dipoles in the metal, and that takes work. And then when I reverse the current, there's a physical rotation to rotate the other direction. It takes more work. So there is some energy loss because I have that metal core. That means the inductor is not perfect. It's not going to behave like it has zero resistance. It's going to behave like it has a real resistance. So in our analysis, we're going to have to take into account that the inductor is behaving like an ideal inductor with no resistance, plus a resistive portion. And so we're going to have to find that resistive portion in our work. Okay, staying with the inductor, if the frequency is really high, how is the inductor going to react? Your X becomes really big, and so it's basically a really big impediment if you have a high frequency. So inductors allow low frequencies just fine, but block high frequencies. If you look at the capacitor, it's 1 over frequency. If frequency is approximately 0, what is your reactance for the capacitor? It's going to be approaching infinity. Why? Because a capacitor has no path across it. Charge can't go through a capacitor. It can charge up and discharge, but charge doesn't go through. So at very low frequency, you should have nothing going through there. Hence, a very high reactance. But if you go to really high frequency, what does a capacitor do? It basically behaves like a wire. It just passes the signal right through with very little reactance. So capacitors and inductors are just the opposite in their frequency behavior. Inductors will pass a low frequency, capacitors will pass a high frequency. So if you make a circuit like this, it's going to vary with frequency, and there's going to be some optimal frequency where you have the lowest total impedance. And so we're going to end our experiment by looking at that. We're going to find the situation where Z equals R, that is, XL is equal to XC. So XL minus XC is 0. That's what we call the resonant condition. So we're going to find the condition for resonance, and then we're going to go and we're going to plot the voltage through the resistor, which is equivalent to plotting the current, as we change the frequency to see how it varies. So, making the phasor diagram to do our analysis. Here's showing adding the vectors. Notice I have VL plus R. You measured VL plus R, right? I told you put VL plus little r, didn't I? It's not vertical like VL should be because there's a resistive part. So we're going to have to find what the breakdown is between the actual resistive part and the actual inductive part. So that's the first thing we have to do with those numbers we measured. So we will start, yeah, that's the bottom, just want to make sure. We will start by making a diagram, and for that diagram, we'll have to get you some more paper. Take a sheet of paper and label it so you have each box is 1 volt going vertical and horizontal, and then draw a phasor diagram like that. Got that? Can you go to the back, get some books and start ripping out pages? Yeah, that's okay. So notice I have the voltage across the resistor is on the horizontal axis. It needs to be scaled properly. So what was the voltage across the resistor? Okay, so that means you're going to measure 3.35 volts. So if each box is 1 volt, 3.35 boxes horizontally, and draw that for the voltage across the resistor. Then notice I have 2 circles. The red circle starts at the end of V across the resistor and has the radius of the voltage drop across the inductor. So your voltage drop across the inductor, cheating by looking at her paper, is 12.01 volts. So you're going to use your compass, which in here, I had to pull this out to make it go long enough, and set it. Notice you can loosen it here, adjust it, and then tighten it so it holds its length. Set it so your distance is that 12 volts, and then draw a semicircle that starts at the end of V capital R and has that radius of 12 volts. And then finally, we have the voltage of those 2 combined. The last number we had, which once again cheating here, was 12.62. That was the voltage of the 2 combined. So then I readjust this so it's 12.62 volts, and I draw the quarter circle that goes from the origin out to that distance. Now notice the green arc is the total voltage across the two elements. The red arc is the voltage across the two elements as well. So where the green arc and the red arc meet, that must be where they actually meet. And so then I can break it down into the two components, the resistive part of the inductor and the inductive part of the inductor. So everyone needs to do that, and I'm going to go ahead and explain the next part. Go ahead. Kate.
Is it okay if we run off the x-axis?
You won't.
Well,
Um,
it looks like
you won't because that's vertical.
the
12 is vertical.
inductance.
Oh, yeah, your arc just ends at the end of the
Okay.
page. So once you've drawn that, you'll have what the values are for the voltage across the resistive portion and the voltage across the inductive portion of the inductor. And then go ahead and calculate what the current is in our experiment. How do you know the current? Well, we need to know the resistance. Something Yafet and I didn't do beforehand was actually check the resistance. So let's measure the resistance right about now. So please work Sesame. I don't even remember what resistor Yafet grabbed. We had to grab a couple to get the right value. (9.85 kiloohms. So write that down. Resistance is 9.85 kiloohms. So now you can calculate what the actual current was, the peak current, the peak current in our experiment. And then based on that peak current, you can calculate what the resistance in the inductor was, what the reactance in the inductor was, and using the voltage across the capacitor, capacitors really are ideal, what the reactance of the capacitor was. So you need to get numbers for all of those. Then you make your second diagram, and your second diagram is the one that's going to look like, like this. And draw that second diagram. I know this is, Yafet's not in the room right now. This is back from what I told Yafet. But do V little r first, then V capital L, then V capital R, then V C. When you do this one, scale it so you have -5 and 0 with your paper in portrait mode. That is with the graph paper. With your graph paper like this, put -5, -4, -3, -2, -1. That's where we're taking into account that it goes up to 12 or so. And so if you do that, going -5 up by 1s vertically, and then going across by 1s horizontally, it'll all fit. So you're going to make your graph. Everything has to be measured carefully because in the end you're getting two numbers. You're getting the magnitude of V total that you're going to compare to what we measured for V total. So you'll find a percent error of difference between those. And you're going to get this phase angle phi. So you're going to get those two numbers as your two results that are, the parts you put in your results section for that part of the experiment. Now, you have some work to do, so I'm going to give you some time. When somebody has their values for the inductance and the inductive reactance and the capacitive reactance,